Welcome back to the Deep Dive. This is where we like to take questions that maybe sound a bit ridiculous at first glance.
Right, the kind of thing a kid might ask.
Exactly. Questions maybe you first thought of as a child, and then we throw some serious science at them. Heavy-duty scientific rigor.
Find some serious answers, even if they often turn out to be pretty catastrophic.
That seems to be a running theme.
It does. So our mission today, really, is exploring the fundamental laws of nature, pushing them right to their breaking points.
And our source material for this comes from a former NASA roboticist, which is already interesting.
Yeah, someone who actually works with stick figure comics but applies, serious computational physics. It's a great combination.
It's the perfect lens for these kinds of extreme hypotheticals, isn't it?
Absolutely.
I love that origin story, too, because it gets to the heart of, well, good science, right? Trying to find answers. Our source mentions the author as a child, asking something like, are there more soft things or hard things in the world?
Yeah. A simple question, but how do you even quantify that?
Right. He didn't have the math then, obviously, but that spirit, that drive to answer any question, no matter how, maybe stupid it seems initially.
That's where discovery comes from. Often those are the questions that lead you down the most interesting paths.
You end up with some really profound insights.
It's absolutely true. By simulating these wild scenarios, violating planetary stability, pushing energy way beyond comprehension, messing with constants like density,
You really start to appreciate how complex and maybe fragile the physics holding our everyday reality together actually is.
Exactly. We're basically stress testing reality itself today.
Okay, let's dive in then. We're starting big. Planet scale changes.
Right off the bat, yeah.
Hypotheticals that just fundamentally alter our world instantly.
Yeah.
First up, the sudden global windstorm.
Okay. The premise here is scientifically quite simple, but profoundly terrifying.
Simple premise, terrifying outcome. Sounds about right.
The Earth instantly stops spinning. Just stops. But inertia means the atmosphere, the oceans, everything not literally bolted to the bedrock.
Including us.
Including us, every building, every car. It all keeps the rotational velocity the planet had, just, milliseconds before the stop.
And that velocity, it's not trivial.
Not at all. Lethal is the word.
If you were standing on the equator, what's the speed? Something like 470 meters per second.
That's right. Which is over 1,000 miles per hour.
1,000 miles per hour. So the air itself, relative to the ground, which is now stationary, it's moving faster than sound.
Supersonic. Instantly.
Wow.
And think about where most people live. That zone between roughly 42 degrees north and 42 degrees south.
That's got to be a huge chunk of the population.
It's about 85% of everyone on Earth. Major cities, New York, Shanghai, Sydney.
All in that zone.
All instantly exposed to supersonic winds. And the rules of aerodynamics, the way we understand air flowing around objects,
They just don't apply anymore.
they completely break down at those speeds. The air doesn't have time to flow nicely around things.
No. So what does it do to, say, a city? It's not just like a really strong hurricane.
Oh, much, much worse. It's not just strong wind, it's active demolition. Annihilation, really.
Yeah, annihilation, okay.
When air moves supersonically, you get these massive shock waves piling up. The air molecules just slam into structures
With incredible force.
far beyond anything engineered to withstand. Concrete, steel, stone, it all just fails instantly.
So how long does this wind last?
Near the surface, friction with the now stationary ground would slow it down pretty quickly, maybe just a few minutes.
But a few minutes is enough.
More than enough time to reduce basically all human structures, skyscrapers, houses, bridges, to pulverized dust and debris.
And it's not just the wind speed, is it? It's what the wind is carrying.
Exactly. You're not just hit by 1,000-mile-an-hour air, you're hit by a 1,000-mile-an-hour abrasive stream of pulverized concrete, steel, shrapnel, bits of tree, everything.
So survival seems unlikely.
On the surface, pretty much zero chance. Safety would only be found deep underground.
Like subway systems, missile silos.
Deep basements, maybe? Our sources actually point to Helsinki, Finland.
Helsinki. Why there?
Because they have this incredible network of subterranean tunnels, utilities, shopping centers, even sports arenas, all carved deep into the bedrock.
Wow. So some pockets might survive the initial blast.
Potentially, yeah. But the wind is just the first killer.
Right, because stopping the planet, That's got to do something to the crust itself, hasn't it?
Oh, absolutely. Think of the crust as this relatively thin, hard shell floating on a much more liquid mantle and core.
And you just slam the brakes on the ship.
Exactly. The internal stresses would be unbelievable. You'd trigger the largest global earthquakes in planetary history.
Everywhere, all at once.
Simultaneously across all continents. And likely massive volcanic eruptions, too, as all that stress finds release points.
Okay, so wind, earthquakes, volcanoes. What's next?
Well, once the initial shock passes, that's when the atmospheric and oceanic effects really get, interesting.
Where does all that energy from the wind actually go? It doesn't just disappear.
Nope. Basic physics. It converts into heat. Over land, friction causes this massive, immediate temperature spike.
Like a heat blast.
A scorching heat blast, yeah. And rapid evaporation from any surface moisture, leading to global, incredibly violent thunderstorms.
Okay, that's over land. What about the oceans? They cover most of the planet.
The wind is so intense it literally churns and atomizes the surface water. For a while, the ocean wouldn't really have a distinct surface.
You mean it would just be a chaotic mix of water and spray?
Yeah, you wouldn't be able to tell where the sea ends and the air begins, just this violent churning layer.
That sounds like a recipe for bizarre weather.
Definitely, because you're mixing everything up. The deep ocean is uniformly cold, around 4 degrees Celsius.
So that cold water gets dragged up.
Violently churned up to meet the superheated air. You'd get this roiling mess of fog, extreme turbulence, rapid temperature swings, just unprecedented unstable weather.
That sounds bad for marine life.
Initially, yes, massive die-offs of surface creatures that need stable temperatures.
Well,
But there's a flip side. That deep water is rich in nutrients that don't usually reach the surface. So after the initial chaos, that upwelling leads to huge chaotic blooms of new life, plankton, things like that.
a cycle of destruction and creation.
In a very extreme way, yes. Meanwhile, the oceans themselves are still moving.
Right, inertia again.
Right.
The water still has that eastward momentum relative to the now still land.
Correct. Which generates a global east-to-west storm surge.
Like a tsunami.
The largest tsunami-like wall of turbulent water in history. Imagine that hitting every single east-facing shore on the planet simultaneously.
How far inland would it go?
Miles. Sweeping many miles inland, finishing off whatever destruction the initial winds might have missed.
Just total coastal devastation.
Globally. And then finally, there's the long-term consequence. The really big climate shift.
Which is?
The end of the day-night cycle as we know it.
Because the Earth isn't spinning anymore.
Exactly. The sun now rises and sets only once per year.
So day is 6 months long and night is 6 months long.
Even at the equator, one side spends half a year baking under relentless sunlight. Water boils off, rock might start to melt.
Then the other side.
Radiates all its heat into space for 6 months. Temperatures plummet so low the atmosphere itself could freeze and fall as snow onto the surface.
Wow, that sounds familiar. Like early Venus or something?
Very much like early Venus, yeah.
Mm-hmm.
Which might have had similar rotational issues leading to extreme temperature differences and runaway greenhouse effects.
Yeah.
Our planet would rapidly become uninhabitable in a completely new way.
Okay, from an instant stop to something more gradual. Let's talk about the expanding Earth.
Right. The premise here is the Earth's mean radius starts expanding by exactly 1 centimeter per second.
1 centimeter per second. Doesn't sound like much.
Initially, no. And it's maintaining its average rock composition, so it's getting bigger and more massive.
Okay, so what happens?
Well, it's a scenario where tiny changes cascade into total failure. The immediate jolt of it starting would be minuscule, you wouldn't feel it. And since the expansion is constant, there's no ongoing acceleration to feel.
It's subtle, sneaky, almost.
Very sneaky. But the first things to notice the effects are technological. Specifically, systems needing extreme accuracy.
Like GPS.
Exactly. Within hours, GPS is useless.
Just from 1 centimeter per second. How?
Because GPS relies fundamentally on general relativity. The satellites experience time slightly faster because they're in weaker gravity than we are on the surface.
Right, time dilation. Engineers have to account for that.
Precisely. They build in these incredibly precise relativistic correction factors into the timing signals. But if the Earth's radius is increasing,
The mass distribution changes, the gravitational potential changes.
even by a tiny amount, yes. That instantly makes all those pre-calculated correction factors wrong. The timing signals, needing picosecond accuracy, just become garbage.
So navigation goes out the window first. What else?
If you had a very precise pendulum clock, like an old grandfather clock, you'd notice it gaining about 3 seconds by the end of the first day.
A direct measure of gravity changing slightly.
Yep, tiny but measurable.
Okay, fast forward a bit. Say 1 month.
After a month, the radius has increased by about 26 kilometers. That's roughly 0.4% bigger.
Still sounds small. Is the gravity change noticeable yet?
Gravity's also increased by about 0.4%, which is still negligible, actually less than the natural gravity difference between cities at different altitudes, like sea level versus Denver.
There's always a but.
But now the structural failures start, because everything is being stretched.
Stretched.
Imagine a long concrete bridge, maybe 10 kilometers long. It now has to be 0.4% longer.
Which is 40 meters longer.
40 meters, yeah. Structures are built to handle compression and tension, but not uniform stretching over huge distances like that. They're not designed for it.
So bridges, roads.
We'd see catastrophic failures. Cracks in long concrete structures first, then elevated roads failing, old bridges collapsing, pipelines rupturing. Anything long and rigid is in trouble.
What about things in orbit, like the International Space Station?
They'd need to get out of there fast.
Why? Is the atmosphere reaching them?
Well, the atmosphere is expanding too, making drag slightly worse, but the main issue is the increased gravity.
Pulling them down faster.
Exactly. Their orbits are calculated based on current gravity. If gravity increases, their orbital radius shrinks rapidly. Their orbits become unstable, they'd re-enter or crash much sooner than planned, maybe within months.
Okay, so technology fails, infrastructure crumbles. Let's go further out. A year? 40 years.
After a year, gravity is about 5% stronger. Still may be manageable for humans, but things are getting dicey. 40 years out, though.
That's when it gets really bad.
That's when gravity has effectively tripled.
Tripled.
Yeah, and that's biologically crippling.
Crippling how?
Just walking becomes nearly impossible without some kind of mechanical assistance. Your legs aren't built for 3 times the weight.
What about other life? Trees?
Trees are amazing structures, but they're finely tuned to Earth's gravity.
Yeah.
Triple the gravity, and most large trees would just collapse under their own weight.
And mountains. Hills.
Massive landslides everywhere. The angle of repose, the steepest angle material can sit at without sliding down, depends on gravity. Triple the gravity, and suddenly slopes that were stable for millennia aren't stable anymore. Whole mountainsides would just let go.
And breathing. Does the atmosphere keep up?
That's a key assumption. If the atmosphere doesn't expand perfectly along with the planet's surface, if it stays sort of tethered to the original radius...
Then as the ground moves further out, the air gets thinner at the surface.
Exactly. Air pressure would drop dramatically. So you've got triple gravity making it hard to move, and you can barely breathe. You'd need pressurized habitats pretty quickly.
So triple gravity, thin air, geological chaos, extinction level event, basically.
For most complex life, absolutely guaranteed.
Okay. Our last planet scale one shifts focus. It's less about physics destroying the planet and more about us destroying ourselves through logistics.
The everybody jump scenario.
Every single human gathers in Rhode Island, stands shoulder to shoulder, and on the count of 3, everyone jumps.
This one is brilliant because the physics impact on the Earth is almost zero.
Really? Billions of people jumping.
Earth outweighs all of humanity by something like 10 trillion times.
Okay, that's a big difference.
So if everyone jumps, say, half a meter up, the planet gets pushed down by less than the width of a single atom.
Wow, so the planet literally doesn't even notice.
A tiny pressure pulse spreads through the North American crust and vanishes almost instantly. Negligible.
So the planet is fine, but the people...
That's where the chaos begins. Everyone lands, there's probably this huge, drawn-out roar from billions of voices. Then everyone looks around.
And realizes they're crammed into the smallest U.S. state.
The societal shockwave is immediate. What's the first thing people do?
Pull out their phones.
Exactly. Roughly 5 billion cell phones probably come out instantly, taking pictures, texting family, calling for help.
And the networks.
Total instantaneous collapse. Every tower overloaded. Complete communication blackout. Just no signal everywhere.
Okay, so no calling for help. What about the rest of the world? Everyone just abandoned their posts.
Right. The entire global support system vanishes overnight. Power grids fail within hours. No one's managing fuel supplies or load balancing.
Nuclear plants?
They'd likely scram automatically, shut down safely as designed when control is lost. But things like water purification, automated farms, shipping, logistics, it all just stops.
The world instantly becomes ruined.
Pristine ruins, yeah. Everything's still there, just completely unmaintained and non-functional.
And back in Rhode Island.
Unimaginable horror, basically. Transportation grinds to a halt instantly. I-95, 195, 295 just become the world's biggest, most permanent parking lot.
Food, water.
fresh water is the absolute critical resource with that density of people. Supplies exhausted or contaminated almost immediately. Stores looted in minutes. Sanitation breaks down. Disease spreads like wildfire. Violence erupts over dwindling resources.
So the outcome?
Our sources predict that within weeks, Rhode Island is essentially a graveyard containing billions of people. Starvation, disease, conflict.
And any survivors?
The few survivors would eventually spread out into this empty, silent world full of derelict infrastructure. They'd be like pioneers starting over, building a new civilization on the wreckage of the old one.
All while the Earth continues its orbit, completely unfazed by the jump itself.
Utterly unfazed. It highlights that sometimes the sociological consequences of a hypothetical are far more devastating than the physical ones.
Okay, so connecting these massive ideas, they really show the almost unbelievable power locked up in basic concepts like mass, velocity, density.
Exactly. And when you take those extreme forces and apply them to small, everyday objects, well, that's when things get really interesting and you challenge physics in a different way.
Which brings us to section 2, extremes of kinetic energy and density, starting with the supersonic baseball.
Or rather, the relativistic baseball. The scenario is a pitcher throwing a baseball at, say, 90% the speed of light.
90%. Okay, that's fast.
That's way beyond just fast. At that speed, normal aerodynamics is irrelevant.
What happens instead?
The air molecules in front of the ball don't have time to get pushed aside. The ball is moving so incredibly fast that it slams into them with enough force to cause nuclear fusion.
Fusion, like in the sun.
On a tiny, continuous scale, yes. The ball's surface atoms fuse with the air molecules, nitrogen, oxygen, and each fusion event releases a burst of energy.
What kind of energy?
High-energy gamma rays, X-rays, scattered particles. It's incredibly violent.
Okay, so fusion is happening all along the ball's path. What does that do?
Two main things. First, the air in the stadium along the ball's path instantly turns into an expanding bubble of incandescent plasma. Superheated, ionized gas tearing through the normal air.
And second?
That constant stream of fusion energy exploding forwards acts like thrust, but in reverse.
Like a rocket slowing it down.
Exactly, like a rocket flying tail first. The fusion blast actually pushes against the ball's motion, slowing it down significantly even as it travels towards the plate.
But the plasma bubble keeps expanding.
Oh, yeah. That wall of plasma expands outwards from the pitch path at nearly the speed of light itself, just fractionally behind the ball. It hits the batter, the catcher, the stands almost instantly.
And the impact, when the ball, or what's left of it, arrives.
Colossal. The total energy release is comparable to a small nuclear weapon.
Though the stadium.
Gone. Everything within about a mile radius is leveled instantly, followed by a massive firestorm that would engulf much of the city, ignited by that initial heat and plasma pulse.
And where the pitcher's mound and home plate were.
You'd find a sizable crater, probably centered a few hundred feet behind where the backstop used to be.
Just incredible destruction. But there's a punchline, isn't there?
The best part. According to the official Major League Baseball rules, specifically Rule 6.08b,
Yes.
if a pitched ball touches the batter advances to first base.
Wait. So after the fusion, the plasma, the crater, the firestorm, the batter is legally considered hit by pitch.
Technically, yes. He gets to advance to first base, assuming first base still exists.
That's beautifully absurd.
It's the ultimate triumph of bureaucratic rules over the laws of physics. Just highlights the disconnect.
Now, you mentioned this is very different from, say, a hockey puck, even a really fast one.
Right, a crucial distinction. To get that fusion effect, you need speeds approaching the speed of light,
Right.
where relativistic effects like mass increasing become significant.
A hockey puck at Mach 8, while fast, isn't relativistic.
Not even close. A puck at Mach 8 has a lot of kinetic energy, sure, but not nearly enough for fusion. It would just hit the goalie or the boards and basically disintegrate violently.
An explosion.
More like the force of a small stick of dynamite, or maybe like throwing a ripe tomato really hard at a wall. Messy, potentially harmful up close, but not a city-leveling fusion event. Different physics entirely.
Got it. Okay. From kinetic energy extremes to density extremes. The neutron bullet.
This one really messes with your intuition about gravity.
The premise is a 1 centimeter cube of neutron star material.
Which sounds tiny, 1 centimeter, but neutron star material is unbelievably dense. It's basically like an atomic nucleus scaled up to city size, pure neutrons packed together.
And how much does this 1 cubic centimeter weigh?
About 100 million tons.
100 million
Right.
tons in a sugar cube.
Roughly the mass of all the great ships of the world combined, squeezed into that tiny volume.
Okay, so if you just dropped it near the surface of the Earth.
Before it even hits the ground, its gravity is so intense and localized, it yanks up a huge clump of dirt, rock, debris right off the ground towards it.
So it doesn't make a clean impact crater.
No, it doesn't punch a hole. It leaves this jumbled, fractured mess, almost like the ground was sucked upwards just before the bullet passed through.
And then
It passes straight through the Earth's crust, like straight through rock. It wouldn't destroy the planet, but it would crush and vaporize the rock directly in its path.
leaving what behind?
A trail of super hot plasma as it goes. An underground shooting star, basically. Unheard of.
And where does it stop?
It wouldn't stop until it reached the center of the Earth, the dense nickel-iron core. Its own gravity would pull it there, and it would just lodge itself permanently in the core.
Okay, but the source asks a fun question. Can you touch it? If it was just sitting there, say, on a super strong pedestal.
That's where the gravity gradient becomes the killer.
Gradient, meaning the difference in gravity over distance.
Exactly. Gravity falls off with the square of the distance. For normal objects, that change is tiny over the length of your arm, but for something this dense...
The change is huge over small distances.
Immense. If you're 10 meters away, you might just feel a slight pull, like standing on a gentle slope towards it.
But as you get closer,
That slope steepens dramatically. The force becomes incredibly focused. Our sources calculate the point of no return is about 20 centimeters away, about 8 inches.
what happens if your hand crosses that line?
The difference in gravitational pull between your fingertips and, say, your elbow, or even just across your hand, becomes enormous. The force pulling your fingers forward is stronger than the force pulling your wrist.
So it just rips your arm apart.
Stretches and pulls it apart, yes. And it's not just your arm. Depending on how you approach, the gravity focusing on your head could make it effectively weigh hundreds of pounds, causing blood to rush violently towards it or away from it. Massive circulatory failure, tidal forces tearing you apart before you even make contact.
Okay, so touching it directly is a bad idea.
Very bad. But there's a clever physics solution if you really wanted to interact with it.
How?
Buoyancy. You submerge the neutron bullet in a pool of very dense liquid.
Like mercury.
Or maybe, as the source suggests for fun, a carefully calibrated mix of salt water and vodka to get the right density.
Okay. Dense liquid. How does that help?
The liquid exerts pressure equally on all sides of your hand and on the bullet. This pressure balances out the intense, rapidly changing gravitational pull. The buoyancy effect cancels the dangerous gradient.
So you could wave your hand around it in the liquid.
Relatively safely, yes. The net force on any part of your body would be much more manageable because the liquid pressure provides a counteracting force. It's an elegant solution.
Very clever. Okay, next up on the scale of weirdness. A mole of moles.
And we mean the furry critter, not the chemical unit, although we need the chemical unit to define how many.
Right. Avogadro's number of moles. 6.022 times 10 of them.
That is a lot of moles.
How much mass are we talking?
It works out to about $4.05 times 10 kilograms, which is actually a bit over half the mass of our moon.
Half the moon's mass
Oh.
in moles.
Yep. If you just released them all here on Earth, they'd cover the entire surface 80 kilometers deep before gravity compressed them. So that's not practical.
So you'd have to assemble them in space.
Exactly. Their own collective gravity would pull them together into a sphere, a self-gravitating mole planet.
What would the radius of this mole planet be?
About 2,210 kilometers, a bit smaller than our moon.
Okay, so we have a planet made of moles. What's the geology like?
It's fascinatingly grim. The internal pressure in the core would be immense, over 100 megapascals.
Which is like deep ocean pressure.
Equivalent to being maybe 10 kilometers underwater, yeah. That pressure would instantly kill any bacteria within the moles.
So no decomposition in the core.
It would be completely sterilized mole mush under pressure. But near the surface, it's different.
What happens at the surface?
It's radiating heat into cold space, so the outer layer would freeze solid, forming a literal insulating fur coat of frozen moles around the planet.
A frozen fur coat.
Oh, okay.
And deep inside, where the pressure is highest, what happens to the water in the moles' bodies?
It doesn't just freeze into normal ice high, as we call it. Under that extreme pressure, water molecules are forced into different, denser crystalline structures.
Exotic forms of ice.
Exactly. You'd get layers of things like ice third, ice V, maybe even ice and ice deep down. These are forms of ice that only exist under tremendous pressure, even at relatively low temperatures.
Ice IX. Wasn't that the stuff in Vonnegut's Cat's Cradle that froze the world?
Ah, good catch. Yes, but the real ice IX is actually only stable at very low temperatures and high pressures. It wouldn't trigger a global freezing catastrophe like in the book. Still, pretty exotic stuff for a planetary core.
So the core is sterilized mole mush and exotic ices. What's the long-term fate?
Over geological time, assuming there's some internal heat from pressure or maybe trace radioactivity, that organic mush would break down
Into what?
into kerogen. It's a waxy, solid, organic substance. It's the precursor material that, under more heat and pressure, eventually forms oil and natural gas here on Earth.
So the mole planet would eventually become an oil planet.
A massive, dark, probably very oily sphere covered in a frozen fur coat, definitely defying normal planetary classification.
The conclusion from the source is quite something too.
Yeah, basically, if you really want a mole of moles, don't try to collect them now. Build a spaceship, colonize the galaxy, let small mammals reproduce across countless worlds for millions of years.
And eventually, the total number of small mammals that have ever lived might surpass Avogadro's number.
It's theoretically possible, yeah. A rather long-term project.
Indeed. Okay, let's pivot now from these huge cosmic forces and critter planets
To things that affect us a bit more directly. Human biology, society, information.
how our own systems, biological or technological, handle extreme disruption.
Exactly. What happens when you remove a fundamental building block?
Which brings us to section 3, starting with life without DNA. What if, suddenly, all the DNA in your body just vanished?
Poof. Gone. The first effect is actually mass loss.
Mass loss. DNA is heavy.
Relatively speaking, yes. It makes up a significant fraction of your cell mass. Losing it all at once means you'd instantly lose about a third of your total body mass.
Would you feel that?
Maybe a slight twitch in your muscles. They're used to pulling a certain mass. Suddenly that mass changes, so they might contract a tiny bit differently for a split second. But after that initial moment, you'd probably feel normal. Temporarily.
Temporarily. Because the real effects are internal and delayed.
Extremely delayed and utterly catastrophic. Losing your DNA essentially mimics the effects of very high-dose chemotherapy, like drugs such as doxorubicin, which work by damaging DNA, or severe acute radiation poisoning.
Why radiation? What's the connection?
Because the reason high doses of radiation are so deadly is that they preferentially damage the DNA in rapidly dividing cells. And without DNA at all, those cells are the first to fail.
Which cells divide fastest?
The stem cells in your bone marrow, the ones making all your blood cells, red, white, platelets, and the cells lining your entire digestive tract from stomach to intestines, which are constantly being replaced.
So what are the symptoms when those fail?
Initially, nausea, vomiting, diarrhea, abdominal pain, very similar to severe radiation sickness or chemo side effects. This is as the stomach and intestinal lining starts to break down.
And this leads into what they call the walking ghost phase.
That's right. You might feel deceptively okay for a short period, maybe hours or a day, but internally, your body is falling apart because it can't replenish critical cells.
Like white blood cells.
Exactly. No new white blood cells means your immune system collapses completely, very rapidly. No new platelets means you can't clot blood. No new red blood cells means oxygen transport fails. No new gut lining means internal bleeding and fluid loss.
So the actual cause of death.
Primarily, it would be overwhelming systemic infection or sepsis. With no immune system, even common bacteria normally living on your skin or in your gut become lethal invaders. Plus, organ failure due to lack of repair and internal hemorrhaging.
How long did this take?
It would be incredibly fast. Death within days, potentially even hours, once the symptoms really kick in. Total immune failure and multi-organ collapse.
Grim. But the source found a sort of philosophical, dark upside.
A very dark one, yeah. In some hypothetical dystopian future that relies on genetic tracking for surveillance and control.
A DNA-less person would be invisible.
Completely off the grid. Ultimate genetic anonymity, achieved at the cost of, well, imminent death. A fleeting freedom.
Okay. Moving from biological data to digital data.
Yeah.
And digital death. The Facebook of the dead.
This is less a hypothetical and more of a demographic inevitability for any long-lasting social network.
The question is, when will the number of dead users on Facebook outnumber the living users?
It's going to happen. The death rate of users is already significant, millions per year globally. And critically, the early adopter generations are now aging.
So that death rate is accelerating.
Projections show it doubling roughly every 7 years for the next few decades. It's a steep curve upwards.
So when's the crossover? When do the dead take over Facebook?
It depends entirely on Facebook's future growth and relevance. If it starts losing users, if younger generations move elsewhere and it doesn't regain market share. Then the crossover point, where dead profiles outnumber active living ones, is estimated to be around 2065.
But what if Facebook endures?
Ew.
Becomes like basic internet infrastructure.
If it becomes something ubiquitous and permanent, like email protocols or TCP/IP itself, something everyone uses regardless of trends, then the date gets pushed back, maybe into the mid-2100s.
But eventually the dead win?
Demographically, yes, unless the platform dies first. And this whole scenario raises huge issues society is only just starting to grapple with.
Like what happens to all that data, those profiles?
Exactly. What are the social norms for memorial pages? Who gets access to a deceased person's private messages or photos? There's immense emotional value there, sometimes legal or financial value, too.
And dealing with negative stuff, trolling memorial pages.
That's already happening. How do platforms manage that? How do families handle digital estates? We're figuring out the rules for digital death and digital legacy right now, often through corporate policy changes and messy legal cases.
It fundamentally changes the nature of the platform, doesn't it? From a live social network to
the largest digital graveyard and unplanned historical archive in human history. A massive repository of personal histories, interactions, photos.
managed by a private company, according to shifting policies.
Precisely. It's a huge, complex challenge for the future, how we handle digital mortality and remembrance.
Okay, our last item in this section looks at what lasts when we don't. Infrastructure persistence after humanity vanishes. The last artificial light.
If humans just disappeared instantly, blinked out of existence, how long would the lights stay on?
Not long for the main grid, I imagine.
Very quickly, no. Fossil fuel plants need constant supply chains, management, maintenance. They'd shut down within hours or days.
Leading to blackouts.
Cascading failures, yeah. One plant goes offline, it overloads others, tripping safety mechanisms. You'd get a rolling global blackout pretty rapidly. Days, maybe a week at most for the interconnected grids.
But some power sources are more autonomous.
Some are. Wind turbines might spin for a while, maybe a few years, before mechanical failure, gearbox issues, lack of lubrication stops them. Geothermal could run longer.
What about hydro dams? They seem pretty robust.
Hydro dams are probably the longest-lasting large-scale power source. They can often manage water flow automatically. A huge, well-maintained dam like Hoover.
How long could that run?
Estimates vary, but maybe several years, potentially even a decade or more, before major mechanical failure or something like sediment buildup clogging the intakes finally stops it.
Okay, so grid power is gone relatively quickly. What about battery-powered lights? Flashlights, emergency lights.
Most consumer batteries self-discharge over time. You'd see those lights dim and die out within, say, 1 to 2 decades. There are exceptions, though.
Like that bell in Oxford.
The Oxford electric bell, yeah. It's been ringing continuously since 1840, powered by an early type of battery called a dry pile. It uses an incredibly tiny amount of power, so some specialized low-power things might last longer.
But for bright lights, we need something else. Space.
Spacecraft are the real long-term contenders, especially those powered by RTGs.
RTGs, remind us what those are.
Radioisotope thermoelectric generators. They're basically nuclear batteries. They use the heat from the natural decay of a radioactive material, usually plutonium-238.
To generate electricity.
Directly, yeah. No moving parts. Very reliable. Probes like Voyager, Cassini, rovers like Curiosity use them.
And how long do they last?
The plutonium has a long half-life. They can generate power for decades, even centuries. The probes themselves might function for, well, potentially millions of years drifting in space.
Until what happens?
Eventually, space debris. Micrometeorite impacts would degrade them or destroy them over vast timescales. But they're the longest functioning artificial lights.
But the source identifies the absolute last artificial light source.
Yeah.
And it's not in space. It's something much closer to home and kind of grim.
Yeah, the final faint glow of humanity's presence wouldn't be a proud monument or a functioning machine. It would be the light generated by our most toxic waste.
Spent nuclear fuel.
Spent nuclear fuel stored deep underground in cooling pools or concrete casks. Centuries after we're gone, it's still intensely radioactive.
And that radioactivity creates light. How?
Through something called Cherenkov radiation.
Cherenkov radiation. Okay, what is that?
It's like an optical sonic boom. When high-energy charged particles emitted by the decaying fuel travel through a medium like water faster than the speed of light in that medium.
Wait, faster than light? I thought that was impossible.
Faster than light in that specific material, like water or air. Light slows down when it passes through stuff. So these particles can exceed the local speed of light.
And when they do,
They create a shock wave of photons, visible as a distinct, eerie blue glow.
so the last light is this faint blue glow coming from nuclear waste storage sites.
Persisting for centuries, maybe even millennia, long after all other lights have gone out. A beautiful, terrifying, and strangely poetic end to our illumination.
Wow. Okay, that really makes you think about legacy, which leads us nicely into the next section. How do we apply these extreme calculations to more everyday things?
Right. How do these massive energy scales relate to common objects and actions? Can we use these principles to gain insight into the energy around us?
Starting with a very British problem, stirring tea to a boil.
Can you actually boil a cup of tea just by stirring it really, really hard?
It feels like you should be able to, right? You're adding energy. Friction creates heat.
Logically, yes, you are adding energy, but the amount of energy is the problem, even if you stir incredibly vigorously.
How much heat are we talking?
The power input is minuscule, on the order of maybe a 10 millionth of a watt, completely negligible compared to the heat loss to the surroundings.
The source mentions Niagara Falls.
Yeah, even the huge potential energy conversion from water falling that far only heats the water by a tiny fraction of a degree Celsius. The scale of energy needed is vast.
So to actually boil a cup of tea, say in 2 minutes, just by stirring, how much power would you need?
You'd need to be putting about 700 watts of continuous power into that teacup via stirring.
700 watts. That's like...
That's about 1 horsepower, continuously, delivered by a spoon.
Okay, no human can do that.
Not even close. But even if you built a machine, a super stir,
It still wouldn't work. Why not?
fluid dynamics and thermodynamics conspire against you.
How so?
At the speeds needed to input that much energy, churning the spoon tens of thousands of times per second, 2 things happen. First, cavitation.
Cavitation, like with propellers.
Exactly. The pressure behind the rapidly moving spoon drops so low that the water boils locally, forming vapor bubbles, a vacuum pocket. The spoon ends up just churning through vapor, not efficiently transferring energy to the bulk liquid.
Okay, so stirring becomes ineffective. What's the second thing?
Increased cooling. All that violent motion dramatically increases the surface area of the tea exposed to the air. Think of all the splashing and churning.
More surface area means faster heat loss.
Much faster evaporation and convection. The rate of cooling would vastly overwhelm the tiny rate of heat being added by friction, even with your 1 horsepower spoon machine.
So the harder you stir,
the faster it cools down, paradoxically. You simply cannot overcome thermodynamics this way. Boiling tea requires a kettle, not just enthusiasm.
lesson learned. Okay, next energy extreme, the lethal dose of neutrinos.
This one is fascinating because neutrinos are famously elusive, ghostly particles.
Right. Trillions pass through your hand every second from the sun, but maybe only 1 interacts with an atom in your body every few years.
They barely interact with matter at all, so the idea of them delivering a lethal dose of radiation seems impossible.
But the key is the source, right? Where do you get that many neutrinos?
You need something truly extreme. You need a core collapse supernova.
How powerful is a supernova in neutrino terms?
The numbers are mind-boggling. A supernova releases something like 10 50-cent neutrinos in just a few seconds.
10 to the 57th. That's a one with 57 zeros.
It's an astronomical number. The energy released just in neutrinos during those few seconds dwarfs the total energy the sun will release over its entire multi-billion-year lifetime.
Wow. So if you have that many neutrinos flooding past...
Even though the probability of any one neutrino interacting is tiny, the sheer quantity means enough will interact to cause significant biological damage.
How close would you need to be to get a lethal dose from just the neutrinos?
The calculation shows you'd receive a fatal radiation dose, about 4 sieverts, from neutrinos alone if you were roughly at the distance of Mars from the exploding star.
That far out, Mars's orbit.
Yes. Now, obviously, at that distance, you'd have already been vaporized by the initial gamma ray burst, the shock wave, the heat.
Right, you wouldn't be around to worry about the
But
neutrinos.
purely hypothetically, if you could somehow survive everything else, the neutrino flood itself would be dense enough to kill you even out there.
What about closer, say Earth's distance 1 AU?
Even at 1 AU, again, assuming you magically survive the blast, the neutrino flux is still high enough to deliver a lethal dose. It's just an incredible demonstration of the sheer power locked within stellar collapse.
An invisible, unstoppable wave of particles causing lethal damage.
Pure, silent, astronomical violence. You wouldn't see or feel them, just the cellular damage adding up.
Okay. One last absurd construction project. Building a Lego bridge across the Atlantic.
This is a great one for exploring engineering challenges at scale.
Feasible. Can you even make Lego float?
Well, Lego plastic itself is denser than water, so it sinks. But if you build hollow, sealed structures, you can make them buoyant, like a Lego boat. So, yes, you could theoretically make buoyant bridge sections.
How much Lego would you need just for buoyancy?
To support the weight of one average car, you'd need a Lego structure displacing about 10 cubic meters of water. So a lot of bricks per car space.
Okay, so buoyancy is possible, but tricky.
Mm.
What are the big design flaws?
Several major ones. First, the open ocean. You need the bridge deck to be several meters above the average water level just to clear typical waves, let alone storm surges. That adds height and instability.
Stability would be a nightmare, wouldn't it?
Yep.
Tides, currents.
Huge issue. You'd likely need incredibly long, strong tethers anchoring the buoyant sections down to the seabed, which is kilometers deep in the mid-Atlantic. Massive engineering challenge right there.
And there's a geological problem, too.
The sneakiest problem. The Atlantic Ocean floor is actively spreading. The tectonic plates are moving apart along the mid-Atlantic ridge.
How fast?
It's slow in human terms, but measurable. Our source calculates it's equivalent to the bridge needing to stretch by about one Lego stud's width every 112 days or so.
So you'd need constant repairs.
You'd need crews constantly out there, basically inserting new rows of bricks and building expansion joints just to stop the bridge from ripping itself apart due to plate tectonics.
Yeah, engineering nightmare. What about the cost?
Astronomical doesn't even begin to cover it. Even the absolute simplest, bare-bones design, just a sealed, floating highway, is estimated to cost over $5 trillion.
$5 trillion with a T.
Using trillions upon trillions of Lego blocks, the logistics and cost are just staggering.
And the source puts that cost into perspective beautifully.
Yeah, the punchline is that for significantly less than the $5 trillion Lego bridge,
You could do what?
you could literally buy all the real estate in the entire city of London, valued around $2.1 trillion at the time of the calculation ship at all, building by building, across the Atlantic to New York, reassemble it on a new artificial island.
And then build a much shorter Lego bridge just to connect Manhattan to New London.
Exactly, and you'd still have money left over compared to the transatlantic bridge.
That really says it all, doesn't it?
It puts the absurdity of the scale into sharp focus. Buying London is the cheaper option.
What an incredible tour through the bizarre and the extreme, from planetary destruction to stirring tea and Lego bridges.
It really shows how applying rigorous science to seemingly silly questions can teach you so much about the underlying physics. The principles reveal themselves in surprising ways.
Absolutely. The connections you find are often unexpected and deeply entertaining.
They are. And perhaps to leave our listeners with one final thought. Something connecting tiny, almost arbitrary details to these vast cosmic scales. Consider the old saying about the British Empire.
The sun never sets on the British Empire because it was so vast geographically.
Exactly. Well, technically, because of the handful of small, scattered overseas territories that remain, the sun still hasn't set on it.
Really? Even now?
Even now. The streak of continuous daylight across some British territory persists. And it persists because, for one brief hour each night,
Yes.
the tiny, incredibly remote Pitcairn Islands in the South Pacific are the only British territory left in sunlight.
Pitcairn, isn't that where the bounty mutineers ended up? Population of like 50 people?
Exactly. A population of just a few dozen people on a tiny speck of land are single-handedly keeping that centuries-old saying technically true just by their geographical position relative to the sun's terminator.
Wow, so that streak relies entirely on Pitcairn catching the last rays.
For about an hour every day, yes. And the truly mind-bending part is when this streak will finally end.
When will the sun finally set?
It will only happen potentially many millennia in the future, on the day when a total solar eclipse happens to pass over the Pitcairn Islands at the exact moment they're the only British territory left in daylight.
An eclipse has to perfectly coincide with that one specific hour.
Precisely. It just makes you think about how these tiny, arbitrary geopolitical facts, remnants of history, can intersect with and even defy these huge, predictable cosmic cycles for incredibly long stretches of time.
A microscopic detail holding out against the clockwork of the solar system. That's actually a perfect thought to end on.
Something to mull over.
Absolutely fascinating. Well, we hope you enjoyed this deep dive into the surprisingly serious science behind some wonderfully absurd questions. We'll see you next time.